Good, we can see it now.
Okay, great. So let me get started. Yeah. Okay. So yeah. So I have to start by thanking the organisers for the invitation to talk, and also to start by acknowledging my students Anna and Godwin, who did most of the work aided by their university supervisors. So slide 2. So here's the talk headline. It's time series analysis to understand, predict and control tokamak fusion reactor operation. Now, let me explain why I'm doing this work the way I am. So I have a long-standing interest in time series analysis, so that when I returned to work on a fusion program around 2010, I was keen to exploit this knowledge. Now, there's general agreement that an energy-producing fusion reactor will require a feedback control system. And obviously, if we have an accurate physics-based predictive model for it, so much the better. The original version of this talk, I should explain, was given at a Circuits and Systems conference. So I emphasise the point that the hostile environment in the reactor core means that there will be a relatively small number of diagnostics. In any event, most at that time anyway, most tokamak plasma position control systems were based on circuit models with the plasma represented as a possibly nonlinear circuit element. Anyway, as I've tried to indicate then, and to some extent now still, we don't know how to characterize this element of the circuit very well. We're extrapolating from smaller devices in a situation where turbulence is present. And analogous experience, say, in aircraft design suggests that this is a situation full of risk. So next slide is about how can we minimize this risk. Clearly, it would be helpful to use all the physics knowledge we have. Moreover, although the signals may have large absolute errors, it is often the case that they accurately record the direction of travel. By this I mean, if say the magnetic diagnostic signal increases, then the magnetic field derivative, which it actually diagnoses, is almost certainly increasing too. An important point is that the range of temperature in a reactor core at any one time means that different diagnostics have to be considered. For example, it's much easier to diagnose central core behavior using the soft X-rays you expect at those high temperatures than magnetic signals, which are stronger near the edge. Increased physics input could involve solving a large fluid dynamic or partial differential equation on a large computer, which reminded me that this is exactly what weather forecasters do. So that decade ago, I found out that they predict the sort of things I want to know for a reactor using a technique called data assimilation, hence my participation in this session. Next slide. Okay, so time-honored tradition and the lack of robust and reliable detailed fluid models indicated to me that in a new field for data assimilation, I should start with simple models, with as simple models as I possibly could. And anyway, this was choice was good from the point of giving a talk at a Circuits and Systems meeting, in that many of these models resemble nonlinear circuits. Moreover, I should limit myself initially to improving physics understanding, seeking to confirm the validity of these simple models by parameter fitting. Hence, I found that I needed to do data assimilation with both state and parameter estimation. Next slide, please. So the simplest models are low-order ordinary differential equations. The Lorentz system, 63 system that is, at parameters where there is a strain attractor is the standard test in this kind of work, as already demonstrated by other talks. Probably more relevant to the tokamak problem is the ANAC model I've shown here, capable of generating a range of time series representing soft X-rays and light emission, as shown at right. The variable denoted A is a simple nonlinear oscillator for negative values of the parameter gamma. Note that the simplicity of ANAC comes from making symmetry assumptions, and that these symmetries correspond ultimately to conservation laws. So there is an admittedly limited physical justification for the ANAC model. So next slide. Yeah, so I guess anyway, at this point in the gathering, I don't think I have to say more than models will be fitted to data using the ensemble Kalman filter following Everson's book. Next slide, please. So this slide shows a typical test of the new Python code for NKF analysis against results from the NKF MATLAB code produced by Evanson, Sakov and co-workers. In fact, chaotic time series, if not too noisy, turn out to be relatively easy to assimilate. Other experience with NKF MATLAB going back to 2013 suggested that nonlinear oscillators are harder because they have, well, essentially they remember their initial conditions, leading to a need for a technique to help select starting values. Okay, so next slide. Okay, these sketches show the two optimization algorithms which Anna looked at to help do some initial fitting to the for the parameters and the state. The one on the left is in the classical mold, which using derivative-free optimization, while the CMA-ES on the right can be classified as a machine learning algorithm. Okay, so next slide. So this slide and the next summarize the fuller range of studies to be found in Anna's report. The focus is on the nonlinear oscillator model, which is strongly nonlinear despite the apparently small size of the nonlinear terms coefficient, because the idea is that A of t has to grow to large amplitude before it is stopped by the stabilizing nonlinearity, the cubic nonlinearity. The graph on the left represents a search in a 4D space, that on the right a search in the 2D parameter space only. So the results are consistent with the statement that the stochastic method, that's the CMA-ES, is more likely to succeed, but it is also likely to take 2 orders of magnitude more computing budget. So next slide. So hence, well, because Anna's time was strictly limited on her project, further studies were actually conducted with the faster method. This slide summarizes another study of a nonlinear oscillator where the impacts of sampling frequency and noise level on the initialization algorithm were shown. So that's the, that if you like is the new work that was carried out by Anna to help prepare starting conditions. So next slide, please. So this slide then shows the successful integration of the optimization code DFO /-GN with the ENKF Python data assimilation code from Leeds. The optimization code uses data from the first oscillation to prepare initial conditions for the data assimilation calculation. And so, and what you're seeing there is parameter and state estimation. So there's 2 parameters and two states to be fitted. Next slide. However, partly in the interest of simulating some discussion, there is sadly a correction to make to the work presented at the ISCAS meeting 2 years ago. That's the Circuits and Systems meeting, based on subsequent work by a student, Lucas Benici, who had only just started at the time of the meeting, and had a lengthy struggle in the second half of 2018 to move the new package back onto Linux from Mac OS. Part of the reason for this was his eventual discovery of a bug in the analysis step, after which the joint parameter and state space estimation becomes a lot easier and its solutions more accurate, as indicated there. So final slide. I've shown that my co-workers, mostly the students, have developed open source software for parameter and state estimation of noisy time-dependent systems. So we've carried out studies to try to understand the circumstances under which it will work best. So as you can see, as far as modeling with circuits are concerned, encouraging results for a strongly nonlinear oscillator have been obtained. The software executes very rapidly for ordinary differential equation systems models, which is encouraging for the ultimate application to reactor control. Now for the future, I have another PhD just starting at Leeds, jointly with Steve Tobias, who will be looking at the fitting problem using a range of recently developed machine learning techniques to compare with ENKF Python. And well, why am I here presenting this at an ExCALIBUR meeting? Well, my interest here is to pursue application to ExCALIBUR for data compressions. So this is a technique to, as you can see there, reduce lengthy time series to a couple of parameters, and this data compression is specifically for the communication of data between models of different complexity and dimensionality. I'm saying that's the reason why I'm here today. Right. Thanks everyone.
Thank you very much. You have made up some time, so we just finished at the right time, original time. I cannot see any questions from the audience. Okay. So you actually showed one example where you have just one data wrongly set at 0 and it causes lots of problems. Is that what you intend to show?
Yeah. Well, yes and no. So you can see that the simulation still actually coped with it, and you know, we could argue that in some sense that's actually quite a good test of what you might find in a reactor core, where you might actually have a data point that goes completely haywire because a neutron hit a detector or something at the wrong time. So it's yeah, it did. Yeah. So yeah. So I mean, so I'm very impressed with the ensemble Kalman filter. Yes.
That's right. So are you actually working on the fusion program? Your work, is it related to the fusion study? Yes,
that's right. Yes. So
that's requires the probably the most powerful supercomputers to do simulations, right?
Well, yes. Well, potentially, but obviously we, as you know, our models are not 3D, but they're 5D or 6D, so we're not going to run those in real time for control purposes.
But I suppose the ExCALIBUR program should actually provide that kind of capability to do multi-dimensional simulations. Yeah.
Well, yes. Well, that's what we'd. Well, it's all very well to produce that amount of detail, but you've got to use it, and in fact, you're relatively limited in what controls you've got once the reactions start. Particularly the, it's almost in. You'll have to be very careful to stay away from regions of instability where your controls aren't as fast as the instabilities that might develop.
Great, thank you very much.